World Spaceflight News Special Report. Here's the latest news from our Percy rover on Mars. Newly acquired samples are being described as exciting and compelling by NASA scientists, with strong signals of aromatic organics at a location with all the right ingredients for life. NASA's Perseverance rover is well into its second science campaign, collecting rock core samples from features within an area long considered by scientists to be a top prospect for finding signs of ancient microbial life on Mars. The rover has collected 4 samples from an ancient river delta in the red planet's Jezero crater since July 7, bringing the total count of scientifically compelling rock samples to 12. We picked the Jezero crater for Perseverance to explore because we thought it had the best chance of providing scientifically excellent samples, and now we know we sent the rover to the right location, said Thomas Zerbuchin, NASA's Associate Administrator for Science in Washington. These first 2 science campaigns have yielded an amazing diversity of samples to bring back to Earth by the Mars Sample Return Campaign. 28 miles wide, Jezero crater hosts a delta, an ancient fan-shaped feature that formed about 3.5 billion years ago at the convergence of a Martian river and a lake. Perseverance is currently investigating the delta's sedimentary rocks, formed when particles of various sizes settled in the once watery environment. During its first science campaign, the rover explored the crater's floor, finding igneous rock, which forms deep underground from magma or during volcanic activity at the surface. The delta, with its diverse sedimentary rocks, contrasts beautifully with the igneous rocks, formed from crystallization of magma, discovered on the crater floor, said Perseverance project scientist Ken Farley of Caltech. This juxtaposition provides us with a rich understanding of the geologic history after the crater formed and a diverse sample suite. For example, we found a sandstone that carries grains and rock fragments created far from Jezero crater, and a mudstone that includes intriguing organic compounds. Wildcat Ridge is the name given to a rock about 3 feet wide that likely formed billions of years ago as mud and fine sand settled in an evaporating saltwater lake. On July 20, the rover abraded some of the surface of Wildcat Ridge so it could analyze the area with the instrument called Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, or SHERLOC. SHERLOC's analysis indicates the samples feature a class of organic molecules that are spatially correlated with those of sulfate minerals. Sulfate minerals found in layers of sedimentary rock can yield significant information about the aqueous environments in which they formed. Organic molecules consist of a wide variety of compounds made primarily of carbon and usually include hydrogen and oxygen atoms. They can also contain other elements, such as nitrogen, phosphorus, and sulfur. While there are chemical processes that produce these molecules that don't require life, some of these compounds are the chemical building blocks of life. The presence of these specific molecules is considered to be a potential biosignature, a substance or structure that could be evidence of past life but may also have been produced without the presence of life. In 2013, NASA's Curiosity Mars rover found evidence of organic matter in rock powder samples, and Perseverance has detected organics in Jezero crater before. But unlike that previous discovery, this latest detection was made in an area where, in the distant past, sediment and salts were deposited into a lake under conditions in which life could potentially have existed. In its analysis of Wildcat Ridge, the SHERLOC instrument registered the most abundant organic detections on the mission to date. In the distant past, the sand, mud, and salts that now make up the Wildcat Ridge sample were deposited under conditions where life could potentially have thrived, said Farley. The fact the organic matter was found in such a sedimentary rock, known for preserving fossils of ancient life here on Earth, is important. However, as capable as our instruments aboard Perseverance are, further conclusions regarding what is contained in the Wildcat Ridge sample will have to wait until its return to Earth for in-depth study as part of the agency's Mars sample return campaign. The first step in the return campaign began when Perseverance cored its first rock sample in September 2021. Along with its rock core samples, the rover has collected one atmospheric sample and 2 witness tubes, all of which are stored in the rover's belly. The geologic diversity of the samples already carried in the rover is so good that the rover team is looking into depositing select tubes near the base of the delta in about 2 months. After depositing the cache, the rover will continue its delta explorations. I've studied Martian habitability and geology for much of my career and know firsthand the incredible scientific value of returning a carefully collected set of Mars rocks to Earth, said Lori Leshin, director of NASA's Jet Propulsion Laboratory. That we are weeks from deploying Perseverance's fascinating samples and mere years from bringing them to Earth so scientists can study them in exquisite detail is truly phenomenal. We will learn so much. Reporting from cyberspace, this is correspondent Karen Calvis.
When we've been exploring a region that we call the Delta Front. If I can have that first image, I want to remind everybody that Perseverance is exploring Jezero crater, and this crater held a lake about 3.5 billion years ago, a very large lake, about 40 kilometers across. And the evidence for that is very clear in this first image. On the west side of the image is the crater rim. This is about 1 kilometer high, and you can see that that crater rim is breached by a canyon. That canyon transported water into the lake, and it also transported sediment. And when that sediment was brought into the lake, hit the slack water of the lake, the sediment deposited and formed the delta, the feature that's labeled on this image. That's where we have been working recently. Jezero was selected for this mission because it meets several key mission goals. It allows us to explore an ancient habitable environment. It allows us to seek evidence of possible Martian life in rocks deposited at that time, about 3.5 billion years ago. And I want to emphasize, this mission is not looking for extant life, things that are alive today. Instead, we're looking into the very distant past when Mars's climate was very different than it is today, much more conducive to life. So we are looking for ancient life. And as you already heard from the previous speakers, we are preparing a diverse suite of samples for potential return to Earth by future missions. And I want to emphasize the idea of diversity. The objective of diversity is to allow these samples, when they come back, to be studied for a huge range of topics, not just astrobiology. There are a huge number of questions that can only be answered by samples that are brought back to Earth and investigated in terrestrial laboratories. So I'm happy to say that we have made excellent progress towards achieving the goals that I just laid out. We've also managed to piece together quite a detailed history of Jezero crater, a history that is surprising. It's not exactly what we expected. The image that you see now also shows the route of the Perseverance rover in its 18 months on Mars, the white line. The region with the red star is where Perseverance is today. In the first year of the mission, we undertook what we called the crater floor campaign. That's on the southeast part of this traverse. This is exploring the crater floor, the rocks that are below the delta. And what we found is not what we expected to find. Many of us expected to find out there in the middle of this crater that once held a lake, we expected to find sedimentary rocks deposited in that lake. And instead, what we found is igneous rocks, rocks that were crystallized from a melt. So that suggests a history that is more complicated than we expected. This crater not only held a lake at one point, but prior to that, likely prior to it, it also had active volcanism and possibly even a lava lake filling that crater. So there's some complexity there that we hadn't actually expected. And we acquired some excellent samples of those igneous rocks. And this is an example of why diversity is important. Those igneous rocks will tell us a lot about the early history of a rocky planet, Mars. And in addition, one of the key things that an igneous rock return to Earth will allow us to do is for the first time put a quantitative age on the surface of Mars. This is something that we just infer indirectly at present. So it'll be very important to get quantitative estimates of age on returned igneous rocks. After we finished the crater floor campaign, we drove very quickly in that arc around to where the rover is today at the delta front. If I could have the next slide, please. So the delta front is a scarp cliff about 40 meters high. You can see that we have driven back and forth studying this place. It's a really interesting place. And the reason it's interesting is that the delta is a place where the sedimentary layers deposited in that lake are exposed in cross-section. So rather than just driving around on top of those sedimentary layers, we can actually drive up and see them one by one. If I could have the next image. This is from the area that you're going to hear a lot about. It's called Hogwalla Flat, and you can see two of those sedimentary layers. The area in the background, the cliff-forming layer, that's a sandstone. And then in the material in the foreground that is lighter toned, that's a mudstone. So these are sedimentary layers deposited in the lake that we have spent a considerable amount of time on. This specific area has probably the highest scientific value for exploration of the entire mission. This is the site that brought us to Jezero Crater. This is the place where we have the best chance to explore these ancient sedimentary rocks deposited in the lake. And what you're going to hear is that we have discovered rocks that were deposited in a potentially habitable environment in that lake, and we have been seeking potential biosignatures. I want to be very careful to define potential biosignature. This is something we've discussed a lot on the science team, and I want to make sure everybody understands the concept of potential biosignature. A potential biosignature is something that may have been produced by life, but also could have been produced in the absence of life. The key point about a potential biosignature is it compels further investigation to draw a conclusion. This is the way science works. We don't always know the answer. We have hypotheses. And the rocks that we have been investigating on the delta have the highest concentration of organic matter that we have yet found on the mission. You're going to hear more about that. And of course, organic molecules are the building blocks of life. So this is all very interesting in that we have rocks that were deposited in a habitable environment in a lake which carry organic matter. We don't yet know the significance of these findings. These rocks are exactly the kind of rocks we came to investigate, both with the rover and its scientific instruments, and also to bring back to Earth so that they can be studied in terrestrial laboratories. So time will tell what is in these rocks. So overall, I want to emphasize that the mission is proceeding extremely well. We are making very good progress at understanding the geologic history, finding some surprises in the history of the crater. And we are also making good progress in collecting this suite of samples for the Mars sample return effort. And what you're going to hear is that the suite of samples that we have collected so far is sufficiently good that we are now considering them putting down a subset of them on the surface of Mars as a target for the future missions to pick up and bring back.
Something in the order of 5 months exploring this delta front region, and you saw the rover traverse in that first map that he showed. This image that you're looking at I like very much because the team worked very hard to find 2 different types of samples to collect from the delta front, and we ended up finding them only about 20 meters apart. These 2 rocks, named Skinner Ridge on the right and Wildcat Ridge on the left, are very different. They each have high science value for quite different purposes that I'm going to explain. Skinner Ridge, as Ken mentioned, is a sandstone. It's a fine to medium-grained sandstone. It contains, importantly, a quite diverse mixture of lithologies, meaning that it has a whole bunch of rocky material that was potentially transported into Jezero Crater from hundreds of kilometers outside Jezero. That's important because this is giving us material from a very far distance that the rover will not visit in this mission. Wildcat Ridge on the left, on the other hand, is a very different type of sedimentary rock. It is a fine-grained sulfate-bearing mudstone that also contains clays. And interestingly, this appears to have formed in salty water, possibly during the lake evaporation stage. So at some point, the lake filled up with water, and as that evaporated, it appears that this rock on the left formed. This is really important that this has sulfate in it and also clays, because that means that this rock has high potential for biosignature preservation, meaning that if there were biosignatures in this vicinity when that rock formed, this is precisely the type of material that will preserve that for us to study when they come back to Earth. So what we have here is both of these rocks are composed of sediments that were transported by liquid water. They were both deposited into a lake, and then they subsequently experienced aqueous alterations also involving water, and cementation after deposition. Thus, these rocks formed in and record conditions of a habitable environment. The next slide, please. In this image, you can see the layering that Ken mentioned up on Rocky Top, and I'm just showing you this because you can see the rover arm, and you can see Skinner Ridge in the lower part of this image. And if you look, you'll notice that there is an abrasion patch. There's a very light-colored circular position in that rock that I'm going to zoom in now. So if we can have the next slide. And what you're seeing here is a close-up Watson image of this abrasion patch. And every time I look at this sort of image, let's remark on how absolutely wonderful this is. We were looking at a very, very small region of space. Notice the 5mm scale bar. This is on Mars, right? And we're looking, and Sunanda is going to show us even a higher resolution image. We're looking in very, very fine detail. And what I'd like you to notice in this rock is that there are color variations that we can see. And we can also see that there are grains that appear to have been rounded. These indicate that this material, this sediment, these bits of Mars in the rock form have been transported down a river and deposited into Jezreel Lake. Can I have the next slide, please? And this image here is just showing that the two cores that we collected from that rock are absolutely fantastic. It does not get any better than this. What you're looking at is the bottom of the core after we drilled it out of the rock, and both of these cores are full. They're as nice of a core as we have collected on this mission. And importantly, these materials will enable all sorts of science to happen, as Ken mentioned, upon return to Earth in laboratories on Earth. And importantly, we can determine when each one of these little bits of rocky material crystallized in this rock. In addition to that, we can also determine when the cementation, when this rock was cemented together in principle. We can learn a lot about the chemistry of the fluids that transported this rock, things like the temperature of that cementation. So we can learn a lot about when this material was deposited. Can I have the next slide, please? So this is now showing an image of the Wildcat Ridge, the other sampling location. And what you see in this image are the abrasion, that circle on the right, that we'll hear more about from Sunanda in a minute, and those two core locations on the left. So once again, we had an absolutely successful coring at this rock. Can I have the next slide, please? And these are the two cores from this rock. Again, the cores are both full. These are essentially slam dunk in terms of coring these two very important rocks at the front of the delta. Can I have the next slide, please? And now when you look at the close-up Watson image on the right of the Wildcat Ridge, I hope that you can all see that these are two very different looking rocks. Specifically, you can see that the one on the right is much lighter in color. It's relatively uniform, and it is fine-grained. As I mentioned, it is also rich in sulfates. And all of this is very important because these are the ingredients, these are the qualities of rock that we're looking for that have high potential for biosignature preservation. So to summarize, both of these samples that we've collected from these two rocks record a paleoenvironment and environmental conditions of a thermally habitable environment. Both of these have very high scientific value for the next generation of scientists when these return to Earth to be studied in the laboratories that you've heard about. I think it's safe to say that these are two of the most important samples that we will collect on this mission, and we're all very excited about what we've found.
So the observation of organic matter at Wildcat Ridge was made by one of the instruments that's on the rover arm that you can see highlighted in the image, which is called Sherlock. Sherlock gives multiple types of information. We have color images and black and white images, and also spectra. Spectra are basically signals that result from light interaction with a rock surface. The light that we use is a special type of laser that you can think of as a fancy black light. and it helps us see things in the rock that would otherwise be invisible to us. The images that we take with Sherlock's 2 cameras provide visual context for where the laser hits in a map. So when Sherlock studies a rock surface, it shoots its laser in a pattern across an area that's about the size of a pencil eraser. Can I have the next image? Yeah, so when the laser lights up different components in the rock, that includes chemicals, minerals, and organic matter. And organics, as you heard from Ken, are commonly called the building blocks of life. All life as we know it is made up of organics. But importantly, organic matter can also be made up by processes that are chemical and they're not related to life. So for instance, through water-rock interactions. And it's also found in interstellar dust. By putting together the image and the spectral information it collects, Sherlock can map where organics and minerals are in a rock, which tells us more about how the organic matter was formed, transported, preserved, or concentrated. Organics tend to form clumps. We've seen this on Earth and in Martian meteorites, and unless you can map, you miss some of that key information. This is the first instrument of its kind that's operating on Mars, and it gives us very important information from rocks as they are found in place to support the selection of samples for the return to Earth. So can I have the next slide? Thank you. Sherlock studied the abrasion patch on Wildcat Ridge on 2 different sols, or Martian days, Sol 505 and 513. We performed about 8 scans on the patch overall. The abrasion patch, as a reminder, is on the same rock of where we sample, but it's not the exact same spot. It is a good proxy, however, for what we are picking up in the rock core, and it gives sort of a preview of what might be observed when we bring those samples back to Earth. In Wildcat Ridge, we detected signals that we think are from a class of organic matter called aromatics, which are stable molecules that are made up of carbon and hydrogen and sometimes other elements with ring structures. These signals were present at nearly every single point in every scan. They are also some of the brightest that we've seen thus far on the mission, and they're about 7 times brighter than what we saw at Thornton Gap, which is an abrasion patch on Skinner Ridge. And so the organic signals are also most strongly correlated to a mineral called sulfate that we saw in the rock. This correlation suggests that when the lake was evaporating, both sulfates and organics were deposited, preserved, and concentrated in this area. So while the detection of this class of organics alone does not mean that life was definitively there, this set of observations does start to look like some things that we've seen here on Earth. So on Earth, sulfate deposits are known to preserve organics and can harbor signs of life, which are called biosignatures. This makes these samples and this set of observations some of the most intriguing that we've done so far in the mission, and it fulfills some of the excitement that the team had when we were approaching the Delta Front. So when we put this finding into context of all the other observations we've done with Sherlock so far, which is 13 other targets we've observed through the crater floor and in the delta, it's clear that we are uncovering a bigger story that's happening in Jezero crater. So we found signals that we think are possibly from organic matter on every target that we've observed with Sherlock to date. And this isn't really unexpected. It aligns with what we've learned from studies on Earth and Martian meteorites and from Mars research from our sibling rover Curiosity. However, it does say that organics seem to persist in the very harsh Martian surface environment, which is very exciting for us. And as we've made our way from the landing site to the Delta Front, Sherlock has seen this particular signal associated with sulfates in a couple of other places. So at first we saw this at just a few points in a couple of scans in a couple of targets in the crater floor. And as we're moving into the delta, these sort of hints are becoming stronger and stronger, and to the point that now, as I've said on this rock, we're seeing it in every single point on every scan. And so, to put it simply, if this is a treasure hunt for potential signs of life on another planet, organic matter is a clue, and we're getting stronger and stronger clues as we're moving through our delta campaign. I personally find these results so moving because it feels like we're in the right place with the right tools at a very pivotal moment. Mars 2020 is giving us a better understanding than we've ever had of the Martian surface to select samples for return. And then Mars sample return stands maybe the best chance ever of answering a very profound question: are we alone in the universe? We are building on a legacy of interdisciplinary and multi-scale research that's been taking a progressively closer look at Mars. Our understanding of the planet bridges across scales, from the orbit all the way down to this view that you're seeing from Sherlock, which is one of the closest we've ever had to a rock on the Martian surface. And it really highlights to me that perspective and context bring meaning to our findings. The strength of each instrument on this rover really came into play on this rock. So on Wildcat Ridge, we now have chemical, mineralogical, elemental, textural, color, and stratigraphic data to help provide some context to anchor what our findings are, and this gives the most detailed information possible across scales and observational axes for Mars sample return.
Let me just say that it's very early morning on Mars right now, Sol 559, that's the 559th day of Mars, and Perseverance is probably still fast asleep, awaiting her next command load of things that she'll be doing in the day. Very productive mission so far. We've driven 13 kilometers, over 13 kilometers, that's over 8 miles. And as mentioned before, we have 15 sealed tubes on the rover. So let me just remind folks what a tube actually looks like. And inside these titanium tubes is we can store about a pinky-sized rock right inside there, right? So we have 15 sealed tubes on board the rotor. We brought 43 tubes total. We also have a sealed tube, which is no rock inside, just an atmospheric sample. And we also have 2 witness tubes that are a measure of contamination that we can do along the mission as well. Let me also mention that Ingenuity is also doing very well. That technology demonstration for a helicopter on Mars, only designed for 1 month and has survived 18 months into the mission, which is very exciting for us. It is winter though, and Ingenuity was never designed to live through winter. It has been an energy challenge and we're carefully monitoring that. It does look like the energy is going up for Ingenuity, and we were just last week able to do a short hop of 100 meters showing Ingenuity is fully functional. So we're very happy with that and hope Ingenuity continues along with us in our journey. So let me look at this first graphic here. Ken already showed this with the current rover location and the tracks of the rover exploring the delta front, going back and forth. We've just arrived back at Enchanted Lake here, and our plan for the next 2 months is to get several more samples, a pair of rock samples, as well as a pair of regolith samples, and another witness tube assembly. So this will bring our total of tubes on board the rover of 20 sealed tubes out of the 43. And I mentioned pairs of samples, so let me say a little bit more about that. We've actually had a pairing strategy from the very beginning of the mission. And so every rock we've gone to, we've actually gotten 2 samples from those rocks. And that allows us to have one for an initial cache depot on the surface of Mars that we can put down and then maintain that second sample on board the rover. So in the middle of this graph, this is actually where the possible first drop location for our samples to the first depot that we may form on the surface of Mars. So we go to the next graphic. And so about 2 weeks ago, we took this image looking back at where that potential depot location would actually be. You can see the rover tracks crisscrossing across this area. And one of the notable features about this area is how smooth and flat it is, right? And so over the past 6 months, we've been very closely working with the Mars sample return teams, looking at this area because, of course, they have to have the job of actually successfully landing here and retrieving the samples. And this really is an ideal location. Very flat, very few rocks, a great place to land, and a great place to actually be able to retrieve sample tubes. So we're looking at the potential of putting down 10 to 11 sample tubes here on the surface, and then that would take about 2 months to probably put those samples down and actually carefully document where they are so the future mission can actually find them. So what would happen after we put down that depot would be further exploration, right? We still have a set of samples on board. Where we want to go is up on top of the delta. So this dark black line shows potential traverse paths we're actually looking at to explore the top of the delta, gather more samples, and get all the way over to where the edge of the lake was here in Jezreel crater, shown there near the crater rim on the left of the image. That's probably going to take at least the next year of operations to do that exploration, but we do even want to go farther than that. Let me just remind folks that Curiosity just celebrated the 10th anniversary on Mars, right? And Perseverance is, designed exactly like Curiosity, and we expect a very long mission for Perseverance as well. And so our long-term plan is to climb up the crater rim, to go beyond Jezero, explore and sample the area beyond that, and to have the potential to actually rendezvous with the Mars sample return missions in the future and actually deliver all the samples we've acquired at that time.
As this crater formed, it probably formed about 3.8 billion years ago. It made a big hole, and that hole is filled with material, as I mentioned, but we don't know the origin of that material. But one of the key things that is special about Mars is how long surface features persist. Without plate tectonics and the kinds of reworking that we see on Earth, features last a long time. So as David suggested, there may have been multiple iterations of lake. The lake might have filled and dried up, and then there might have been magmatism filling it up with lava, and then more lake. So all we can really say is that there is evidence that there are igneous rocks that are older than the final iteration of the lake that we see that made the delta. What happened before that, we don't know, but it's basically a time history the bottom of which we see is the igneous rocks, and then the upper part of which is the delta that is the last iteration of the lake.
The way that I think about this is these samples that we've collected, as we presented here today, have ingredients for life in terms of the environmental setting. This material was transported by water, was deposited into a lake. We have fine particles that were settling out of that lake. We have phases that were formed during evaporation of the lake. All of these things, as we've discussed, have high potential for biosignature preservation. If these conditions existed, I think, pretty much anywhere on Earth at any point in time over the last, let's call it 3.5 billion years, I think it's safe to say, or at least assume, that biology would have done its thing and left its mark in these rocks for us to observe. And so that's really why we're so excited to be able to address these questions upon returning these samples to laboratories here on Earth. We have all of the right ingredients here.
And so the plan is that we will, as Rick said, we will explore the top of the delta, probably take us about the next year, and then we'll do that westbound traverse across the units at the margin of the crater. So we're still intending to get there.
It is very fair to say that these already are the most valuable rock samples that have ever been collected. And any state-of-the-art analytical technique that will be available will be applied to these rocks. In terms of your question about the organics, one of the most important things that we can do is look at a very fine scale, at a much finer scale than we're able to with the rover. So, for example, we could look with various in situ measurements to look at the micron scale, where and what type of organics are seen, what minerals are they associated with. That will inform things like were those organics trapped in certain minerals at certain phases, for example, when that rock became cemented, when the sulfate precipitated. There are isotopic measurements that can be made on a fine scale of this sort. There are basic chemistry observations that can be made on a fine scale. So what we can do in a laboratory is obviously much different than what we can do with the rover. Obviously, the instruments that we have in the rover are extraordinary, and the fact that we can make these observations of organic molecules on Mars to begin with is just awesome. But it's really the level of detail spatially that will be different here on Earth.
We have a grid that is laid down on the map of the crater floor, and each box of this grid we have associated with a national park or preserve somewhere in the world. And so we take the names off of a map of that national park or preserve and assign it to the targets. And so we do that with lots of different targets. So you heard us use lots of different names, not just Berry Hollow and Skyland. We have all of these names are pulled off of the map, and the map that we are pulling names off of that you've just been hearing about is Shenandoah National Park in the eastern United States.
If you were betting, would you bet that there's actual biosignatures in these rocks?
Let's just say we are not going to bet. Yeah. We're going to decline.
We're going to look at the data.
Do you see any evidence for any functional groups like amines, halogens, hydroxyls, anything like that? Thank you.
Yeah, that's a really good question. So I'll first start by giving a little more information about Sherlock. So Sherlock doesn't see all organics equally. It has sort of a preference, and aromatics is something that we would sort of preferentially see because there's some enhancement that we have. So that's why we think when it's showing up, and it's showing up so clearly, more likely that it looks like aromatics. And then we also have analog instruments here at JPL and a couple of other places that we have reference libraries that we've built up. So basically every time we get signals, we compare to our reference libraries that we've developed using the analog Sherlock instruments, and then compare to see what those signals look like. So that's why we think that this one is aromatic, because it matches the things that we're seeing in the library.